So the next speaker is Professor Baaquie, and Baaquie is a colleague, very talkative. And I remember when we joined, and Professor Baaquie is always ready to provide advice and help to young faculties like me. And he is also very adventurous. He also started in higher energy physics like Professor Lai. And he worked on string theories. And then he ventured into quantum finance. And he certainly the first physicist work on finance. And just by talking to him, he has been working in Malaysia for 5 years now. He just came back to Singapore, and he's still working. And he had published the book last year, and this is much more than what I can do myself. So let's hear from Baaquie. Right. Sorry, I didn't have any question time for Choi Hing. Probably if anybody wants to have a comment or any addition to what he said, please, this will be the last chance. Okay, maybe after Baaquie's talk.
Can I have a laser pointer?
Yes, this one.
Hello. Am I working? Is it working? Yes. Yeah. Okay. Laser pointer, how does it point? Professor KK Phua, distinguished guests, colleagues, ladies and gentlemen, pleasure to be here to recount my journey in physics and, of course, my interactions with KK. My title is a bit peculiar, but I'll tell you why when I go into it. So I have two parts to my talk, my journey and then my summary of what happens, in my view, in the Department of Physics. So Choi Hing's, talk is a tough act to follow. So I will try and make it interesting. So why do I begin with this, my journey? It's not about me. It turns out that when I got this invitation to give a talk here, I was a bit of a dilemma because KK is a dear friend. In fact, my journey in physics starts with KK in Singapore. I met KK in ICTP. Professor Abdul Salam, our great laureate and common friend, introduced me to KK in 1982. In 83, which is exactly 40 years from today, I came to Singapore on the first Asia-Pacific conference organized by KK, and he invited me to come here. And then in 1984, I joined the Department of Physics, and I was in contact with KK regularly, publishing and being an editor of the journals, and many conferences organized, which really energized me always. Now, the dilemma I had when I had this invitation to discuss 50 years of physics in Singapore is that my work is far from the mainstream. Okay, so I was always off, an outlier doing things which nobody else would do. And so the only way I can actually communicate what physics meant to me, and also it is part of Singapore's history, is to recount my journey and then relate it to the general question of physics in Singapore, and of course, and how KK was fundamental to my journey. So with your kind indulgence, I will recount the various subjects I've studied to show you that physics is not just physics as you think of it. Physics is a vast subject, and it has applications way beyond what you can imagine. At least that's what I found. So my first interesting encounter, I'm a trained as a field theorist, quantum field theory and quantum mechanics. And, the student of Ken Wilson, who is a towering giant in physics. He's a Nobel laureate and all that. So I learned field theory from him. So I had the good fortune of talking to Professor Anthony Leggett, who used to come regularly to Singapore. And talking to him, I came to the following conclusion, and this conclusion is mine, so I don't want to place it on him because he doesn't have to take ownership of this. So my conclusion was, and this is for the physicists in the audience, the degree of freedom, the foundation of quantum mechanics, in principle can never be observed, full stop. Number two, Hilbert space, where the entity lies before you perform measurement, is outside space and time, okay? So what you see here is run by something outside space-time. So this was kind of a radical realization for me. So I said, look, I must write a book to explain and justify this. It's not a crackpot speaking as an amateur. It's based on the mathematical formalism of quantum mechanics. So I wrote a whole book to justify my point of view. And I'm willing to debate this with anybody, okay? This is my take, and it's not over yet because a lot of ramifications come out. Because, I recently wrote a book on quantum computers, and these issues come out with full force there. So it's not something, which is an aside. So this was an interesting journey for me. I did my PhD on lattice quantum fields, and that's a vast and interesting subject. In fact, if you are aware of computational physics, the most powerful computers have been used to study lattice quantum fields. If you want to study quantum fields numerically, especially gauge fields, you have no other way but to study lattice quantum fields, okay? This is the absolutely backbone of high energy physics. So I studied this, and I wrote a book on this because I have a point of view, because I have studied it from my own point of view. So I wrote this book, Lattice Dirac fermions, Lie algebras, Kac-Moody algebras. They're the mathematical foundation of this subject. And then, of course, I studied the renormalization of a lattice quantum field, which is a very complex object, because the vertices, for those who know physics, are very complicated in a lattice theory. And then, 5, 6 terms instead of one term. And then I did this so-called block spin renormalization, which turns out to be one of the most intuitive formulations of a quantum field. If you ask me what is a quantum field, then, the way you explain this is the following, that at every length scale, so you think of a lattice, then you have lattice, you combine them into blocks, and then you integrate out these blocks, replace them with effective degrees of freedom, and so you can increase the spacing of the lattice. That is renormalization. It's a coded, message I'm sending to those who study physics. So if you want to understand renormalization, you must understand block spin renormalization. That's the most intuitive formulation. You can say, well, why do I care about renormalization? Well, if you do any science, you'll discover that this idea permeates all of physics now, and information science, and a lot more. So I had a nice time writing up this topic. Now I came to the issue when I was in the department of what is physics, okay? So, so my conclusion, I'm saying it half seriously, that physics is what physicists do. So you may say, what do you mean by that? What I mean by that is that physics, if you really master physics, it gives you a point of view which is different from those who do not have this point of view. Sounds like a tautology, but it's not. Physics gives you a point of view which you can visit subjects from a complete different perspective and come up with new results. So I'm convinced myself, 21st century physics will be based on the mathematics of quantum mechanics and quantum field theory, full stop. This will permeate every branch of knowledge, arts and science, including philosophy and even religion. Okay, I'll slightly touch on that to show you why. So quantum mathematics, which is the mathematics of quantum mechanics and quantum field, is the foundation of the future of mankind, full stop. I mean, it sounds dogmatic, but it's not. If you look at Newton and calculus permeates all of science. It came from physics, but that just happens to be its origin. So here I applied this idea to various subjects. I started with option pricing. I had the good fortune of meeting an alumni of ours who works in the finance industry, and he told me, option pricing has something called the Feynman-Katz formula. And that, it was a bell which rang in my head, because Feynman-Katz formula is to do with the Feynman path integral. So I studied this subject, and I was fortunate that I had a colleague, Lawrence Ma, from the math department, who has gone over to other subjects. So he educated me on mathematical finance for a year. He would give a seminar every week and really explain to me what this subject is all about. And so I'm indebted to him. So in 1997, I published a paper using path integrals to price options. Options, by the way, the daily amount of options traded today is $450 billion per day. Okay, it has beaten stock prices in terms of the main instrument of finance. So there's not some tertiary, small subject. It's absolutely the backbone of finance today. And notionally, the value of options runs into $600 trillion. It's a vast subject, okay? So I made models for FX and other options, and I had PhD students, Dusin and Pantan, who actually applied these models to the real world, which is market. And we discovered that these models work marvelously well. It's all historical. I'll tell you the shortcoming of these models are later on. Then again, thanks to KK, I did a sabbatical at Harvard University in 1998. He introduced me to Sidney Coleman, who invited me to Harvard. So I was there for a year, and I had the good fortune of making friends with my colleagues in the Harvard Business School. So in talking to them, I realized that the debt market is the bulk of finance. You know, stocks and foreign exchange is 15%. I think 85% of the financial market is bonds, various kinds of bonds, debt market. So I wrote a paper applying quantum field theory to treasury bonds, okay, two vastly different subjects, which I enjoyed. Because when you apply your ideas to a new field, you're a pioneer there, right? So you're really, you know, in unknown territory. And that's where the physics comes in, because physics guides you as to how you view a subject, what you're looking for. And remember, it's all about mathematical modeling. It's not qualitative. So I developed a two-dimensional quantum field theory on the forward interest rates. I remember talking with Choi Heng once, and I was very excited. I just realized what it was. So I showed him on the blackboard. There's a two-dimensional quantum field. So ultimately, you know, as scientists, everything is data. So I developed the theory. Then I had outstanding students, Yu Liang, who runs the hedge fund in Shenzhen now. And with him, we showed that historical data, we could fit to 95% accuracy. I had another collaborator with me, a famous physicist turned finance, Jean-Philippe Bouchot, who has a €5 billion fund he runs in Paris, and he's the chairman of that company. So I had a lot of nice colleagues who helped me enter this field of finance. And it's an ironical coincidence now that, you know, I'll come back to this later, that I became interested in quantum computers recently, and then finance comes back there with full force. I'll tell you why in a minute. And then I have no time to go into this. You know, 5 years in Malaysia, I spent doing Islamic finance, another completely brand new subject, far more complex than mainstream finance. The reason being the following, that in normal finance, mainstream finance, if you have a bond, remember 85% of the market is debt market, the coupons for a mainstream finance instrument are fixed. The coupons are fixed the day you sell the bond. Islamic finance, the coupons themselves are stochastic. They're uncertain. So you have an uncertainty on top of the uncertainty of the forward interest rate, which is a bond. It's a very complex and interesting subject. And I studied that. I have many models on that, but I have no time to discuss that. And then coming back to the mathematical foundation of quantum mechanics, there are two foundations there, path integrals and quantum fields. And they are slightly different. Path integrals deal with finite number of degrees of freedom, or if you like, with quantum mechanics. So again, I taught advanced quantum mechanics for many years at NUS. And so I focused on studying the Feynman path integral because no other module in the department would teach this subject. And I don't think even today they teach it because it's a specialized subject. But in my view, the path integral is the most powerful formalism which has come out from physics. So I wrote a book on this to explain the formalism, why they're so powerful, and what can it do. It can do almost any computation you can imagine. It can't do experiments, okay, clearly. It's a theoretical tool. But besides that, it's an incredibly powerful instrument. So I wrote a book to basically present my view. Being in NUS, obviously I was teaching, right? Teaching is part of our mandate. We must teach. And so I was happy, I was the vice dean of this program, University Scholars Program, which was launched, and I was part of the team which launched it. So we had this view. And then a few years later, I was in a committee which restructured the curriculum of NUS. And we proposed these so-called general education modules to have intellectual broadening for the students of NUS. All science, arts, whoever, should have broadening of the intellect. They should not be specialized on only one topic. So these two pedagogical innovations we made, I thought, since we are talking about it, I have to exemplify it by showing in practice what it means. He's talking like you have intellectual broadening in science. What do you mean by that? So my colleague and myself, we wrote this book which synthesized physics, chemistry, math, and information science, and biology. And I say synthesize. We don't have a chapter of physics and chapter of chemistry. No, we synthesize it like we did photosynthesis, quantum mechanics, biology, action potential, storing chemical potential. So we try to show that science is a seamless entity. We did all of chemistry based on quantum mechanics to show bonding, hydrogen bond, covalent bond, this bond, that bond. All comes out from one underlying theme, which is basically physics. But when you apply it, it has different form. Biology, we did a lot of biology, evolution, genetics, RNA, DNA, very interesting stuff. So I had a lot of fun doing this also. Now, you notice this science we did is intuitive and it was instinctive. But my personal view was the deepest understanding of nature is in physics. And from there, you realize that nature is completely counterintuitive. Whatever you see is completely misleading. That's not what is reality. It's a vague approximation of what really exists. So, for example, curved space-time. You can't see curved space-time. Quantum indeterminacy. You can't see quantum indeterminacy. What does indeterminacy mean? That you're sitting in two chairs at the same time. It seems ridiculous. How can it be possible? Yes, it's possible if you're outside space-time. That's where Hilbert space is. So my view was that intuitive science is great, but counterintuitive science is the actual truth. That's where the real physics and nature come together. So we wrote this book, and we covered what we consider cutting-edge physics, because that's the deepest level of counterintuitive science, from black holes to superstrings, from quarks and gluons to astrophysics and neutron stars and cosmology. So we had a lot of fun writing this book also. Now, I had the good fortune in 2010 to do a sabbatical at University of Leicester in England. And I had some colleagues in economics, and they educated me on mathematical economics. I mean, one thing I found most exciting being a physicist, you must constantly learn new things, okay? If you're just doing one thing all your life, one horse trick, that's boring. You must diversify, you must find new things and must take up new challenges. That'll keep you going, okay? So I discovered that I can model commodities. The foundation of economics is supply and demand. I realized supply equal demand is completely wrong. That's a complete canonical truth in economics even today. So I postulated a potential, supply plus demand. And then I had a path integral for the commodities, okay? And of course, you can say you're a crackpot. Who believes you're right? I said, fine, let's look at data. Data, 95% confirmation of the model's prediction of correlation functions. So physics, it's always about physics, that you have a quantitative model, you must check that empirically. When you do superstring theory, you're far from experiments, because that's a different game going on. But normally physics provides you a lot of data, and data can check your experiment. So I had three outstanding students, Chao Yang, Duxin, and Yu Miao, and they ran my models. We worked together, and and someone asked me, why should this model work? What's the basis? The biggest complaint of economics is that, what's the basis of your postulate? Economic, I say zero. I have no basis of anything. This is from thin air. Let's just see what the model does. Maybe later on you'll find the principle. And you do find. If you don't, who cares? The model works. So that's the physicist's approach. model data verification or falsification, you may fail also. Now, my passion has always been quantum field theory. So I taught quantum field theory for 3 years in NUS, and it gave me a great chance to revisit quantum field theory. So I wrote a textbook on this. This textbook became absurdly long. It's over 700 pages because I did all of quantum fields, and then I added to it applications to economics and finance because people said nobody can understand the application unless you explain it. It's clear to you a forward interest rate is a 2D quantum field. Person who doesn't know any quantum field, for him is gibberish. What do you mean by that? Or even a field theorist can't make the connection, right? So I said, okay, I'll expand the book. So I did all the good things, Feynman diagram, any renormalization, and I did phase transitions, all the stuff we love, but also economics and finance. So I had a lot of fun doing this also. Now in Malaysia, I was happy that, I was teaching mathematical methods for 5 years. So it gave me a chance to do mathematics as such, no quiz. Why was I interested? Because, again, coming back, my passion, of course, is quantum mechanics, quantum fields. So the mathematical basis of these subjects is linear algebra, calculus, theory of probability, differential equations, partial differential equations. You must master these. And then I show in the book that path integrals are natural synthesis of linear algebra and calculus, the two pillars of modern science. If you synthesize these two subjects, you get quantum mathematics. Quantum mathematics is the following. Calculus of one variable, Newton. If you have infinitely many independent variables, what do you have? You have quantum mathematics. That's the mathematics of the future. So how do you organize infinitely many independent variables? Then you have to have quantum fields and things like that. You have to organize these variables. So it's a very natural development of calculus to infinitely many variables. So I explained that in my book. My latest passion, during lockdown, I was happy, Quek and myself were on Zoom, and Quek kindly introduced me to quantum computers, okay, which is, when I was introduced to quantum computers, I was very excited. Because you know why? The only science which had withstood physics was information science and computer science. They were a separate body of knowledge. With quantum computers, you discover that information science and computer science, as is done by the department, is what we call classical information theory. At the tip of the iceberg, quantum computers and quantum algorithm open up a vast new field of algorithm that is unimaginable. I mean, for example, recent experiments have shown these computers are 1 trillion times faster than supercomputers. Not 100, not 10,000, a trillion times faster. So I told Quek, I know nothing about it, let's write a book, because the only way I can understand a subject is if I explain it. So we wrote this book. It just was published last month. It was really a great exercise. I mean, I was happy to write this book also. So all this is coming from physics, by the way. Now, in the end, when I came back from Malaysia, I was a free man. So I said, look, all of this stuff I did in finance was historical data. How about predicting in the real market? How about going to the real market and do commodity price and predict commodity prices? So that's what I'm doing now, okay? So this predictions for commodity prices, again, correlation functions, path integrals. That's how the predictions are made. But the historical models don't work because the parameters are time dependent, and so if you use past, you can't extrapolate to the future. You have to have a new approach. But the mathematics is again back to physics. Now, I'm a real outlier, so I was in sabbatical in France in 2003, and a colleague of mine there said, look, why don't we apply quantum mechanics to human consciousness? I said, yeah, it's a great idea. Why don't we do that? So we wrote a paper, a couple of papers on quantum field, a supersymmetric quantum field theory for human consciousness. You may think, well, this is really crackpot stuff, man. I mean, you can't be serious. So we said, no, experiment. So my colleague in France has a number of colleagues in Switzerland. We did a lot of experiments based on psychological and psychometric testing procedures, which, I'm not an expert on. And so we had a lot of results which we wrote up in a book. Now, I will run through these topics because, I have not much time left. We also applied physics to history. You may say, well, how can history be conceivably linked to physics? Well, a colleague of mine in France has had a new topic called cliophysics, which means recognizing patterns in history. So my favorite subject to studying history is China, because China has a really massive trove of data, historical data, going back 2,000 years, okay? So China, if you want to study history, I recommend study China, because it has a peculiar, unique feature of the rise of empires and then the fall of the empires. Rise of empire, 300 years. Empire falls, 300 years of chaos, civil war, fighting. Again, an empire rises. Again, it falls. So we studied 4 cycles of empires rising and falling and analyzed why does it happen. And we have a solution which I'm not going to give you, okay? We found a pattern which explains why empire rises and why it falls. So my interest continues. So, I wrote a book, and, KK Phua has been kind enough to publish. This book is coming out soon on how China became so powerful so quickly. So, people say, China did this, China did that. I said, look, I'm not judging China. I'm not saying it's good or bad. Put it aside. How did it become powerful in 30 years? What's going on? What's the explanation? So the book explains that, in my view, an explanation. So I didn't stop there. The second book on China is Contemporary China, which I'm still working on, to socialist market economy and private capital. It's a very fascinating subject, because, if you don't study China, you have all of these stereotype ideas that China has become capitalist, China has become this, China has become that. Those are one-liners which make no sense. It's a very complex and a very intricate and a very massive structure in China. You have to study it to understand it. So I enjoy studying China, especially the history of China. I also am interested in philosophy. I have a book here on metaphors and metonyms. For example, I said this in passing, but you can ask, how does the degree of freedom exist if it's never observable in principle? How does it exist? What's its form? You can also ask, how can Hilbert space exist outside space-time? What does exist mean? Those are philosophical questions coming straight from quantum mechanics. The quantum mechanics has introduced to philosophy completely new, what I call ontology and epistemology, which is worth studying. So that's what I'm interested in, and this book is on that. Okay, enough of me. So here is my take on physics in Singapore. So I said all this to tell you physics is not just physics in the lab, okay? That's one kind of physics, which is great. Physics is a vast undertaking, opens your mind to the world in completely different ways. So for many years, I run through physics before 2000 for a specific reason. We had rigid curriculum, everything was locked in, the promotion tenure opaque, research rudimentary. In that environment, KK Phua was a beacon of inspiration for us. He was the incredible energy he had to say, we must be world class, we must be number one, we must be on the world stage. So in that stage, when myself, Choi Heng and Chu Yap, and we were there, and of course Prof Bernatan, we were there, things are very laid back, right? I mean, research was okay, like an aside, and some teaching, and we're sitting in the lab all day. But KK was there pushing us. Every time we did a conference, we had a meeting, we had all the luminaries came in, all the state-of-the-art ideas, and we felt we have to also show what we are doing. I mean, we can't just be, managing the conferences. So at that point, KK, in my view, one of the most powerful driving force in the department to get things done, to get off the ground. So we had curriculum reforms in 2000. The whole NUS was revamped. A lot of stuff was cut out. We had great modules. Physics department launched many gems. We had promotion tenures become more transparent. Great faculty were recruited. Research was emphasized. Papers of high quality came out. It's a great pleasure to see physics grow in stature, world class in 50 years. Alumni, faculty members have won many prizes from NTU and NUS. KK has been a great contributor to these advances. Now, KK's contribution to physics has been recounted, so I can't add much to it. I'll just give you my spin on it. So KK's entrepreneurial abilities really took off, and World Scientific became a world-class publisher. And that's not easy, because Springer, Cambridge, Oxford have been around for hundreds of years. So from nowhere, The new kid on the block became world class. Again, you have to see KK in action to understand. So kind of inexhaustible energy he has outpouring. I mean, now he's 80, but he still has the energy. We wish him many more years. So we were all in awe and admiration of the achievements that he was making. The foundation of IAS in 2005 brought a stream of Nobel laureates. This is his vision, that we must be on the world stage. We must, if you want to be number 2, you'll be number 5. You have to be number 1. Then you have a chance to be actually excellent. If you start off by saying, yeah, well, yeah, I'm second class, buddy, I'm being somewhere in the back row, I'm sitting, you're finished, okay? KK is always, up front, right in the front, up there. So, I went to Princeton, I went to Harvard, I went to Stanford. Everybody knows him in the community. He's one name, they know him. We owe KK a lot, and of course, it's not over. Many more years ahead. I'm happy to recount, in the first journal launched by World Scientific, I was an editor, and I helped KK launch it, wrote the blurb for what should be the editorial guideline for the journal. I'm one of the founding editors of China and the World. This is one of my favorite topics. I wrote 3 papers on this. I'm now also founding editor of, again, World Scientific, of annual reviews of Islamic finance, another totally different topic, which is also equally fascinating. And I published a number of books there. So my conclusion, journey of physics in Singapore has been and continues to be exciting, challenging, and rewarding. The leadership of Singapore, NUS, and physics department in particular is tremendously visionary, and I must express my thanks to them, because they gave me complete support to do whatever I wanted to, never constrained me. In fact, when I first came for the 10, 15 years I was in NUS, I was traveling 6 months a year with the total support of department to visit other centers of physics, to bring back, ideas which were world-class. So KK has played a major role in raising the level of physics in Singapore to world-class levels. I mean, Choi Heng recounted that. I did that briefly. I look forward to many more years of journeying in physics and working together with colleagues, and look forward to KK's continuing sterling leadership. Thank you.